So section 28 is on a summary of curve sketching. So we've done a lot so far in calculus. So we have talked about increasing and decreasing functions, concavity. We've talked about finding maxes and mins, points of inflection, right? We've also talked about horizontal asymptotes. We're putting it all together into one big thing. Okay, so we're going to graph all different types of functions. And you guys do have a quiz on this. Remember coming out in. It's tomorrow, yeah. It's on your little calc due dates. All right, so here are the different steps for sketching a curve. So a lot of this you've done before. You find the domain, you find the first derivative, you find the second derivative. So you're finding where it's increasing, decreasing, max, and min for the first derivative. Concavity for the second derivative and points of inflection. Well, he's going to be looking for that. All right, and then horizontal asymptotes, vertical asymptotes, if there are any. And then we're also going to find x and y intercepts if possible, okay? So we're putting this all together. Now notice I did mention here, though, I said sometimes it can be very time consuming to find the second derivative. So I'm going to talk about when you would want to find the second derivative and when you would not want to, because some of them are kind of crazy, especially if they involve quotient rule and chain rule. It gets a little crazy. All right, so first example, it says sketch the graph of the following function. So we have f of x equals 4x cubed plus 18x squared plus 24x plus 8. So if I'm finding the domain and range, nothing's making this undefined, right? So my domain is definitely negative infinity to infinity. And I have no vertical asymptotes, and I have no horizontal asymptotes, because it's not what we call a rational function. There's no denominator. All right, so I'm going to go ahead and find the first derivative and the second derivative. So my first derivative is going to be 12x squared plus 36x plus 24. And I usually want to find where it's equal to 0, and so on.
Wait, what?
Uh-huh.
I don't know why.
Oh, man. So we pull out the 12. So we have x squared plus 3x plus 2. And we have x plus 2 and x plus 1 when it factors. So our critical values are -2 and -1. So we're going to do what we always do. We're going to put those on a number line. But we're going to try to skip some steps if possible. Okay, so I know what this graph looks like. There's two critical values and it's an x cubed, right? If it's x cubed, it's going to go like this, right? Does that make sense? So can you tell where it's increasing, decreasing, increasing, and so on? Yeah, it's going up, down, and then back up because it had two critical values. If it only had one, then it's just like the parent function y equals x cubed, right? It's just kind of tapering off to a 0 and then going back up. All right, so don't waste time doing those types of things. I mean, if you know what it's going to look like, you don't have to like think about plugging numbers in or whatever. So there's going to be a max at -2, and there's going to be a min at -1. So we're going to go ahead and find those values. So if you find f of -2, you go back to your original, and you plug in -2. And when you plug in -2, you get 0. And then on this other one, if you plug in -1, oh, I can't remember what you get here. -4 plus 18 minus 24 plus 8. -2? All right, so we get that. Okay, so that's the first derivative. And remember, the -2 one is the max, and then -1 one was the min. Okay, so as I'm starting to sketch this out, you guys have a place for your graph. I don't. I have -2 comma 0, and I know it's a max there, so I'm going to draw like a little bump. So I know that's going to go up and hit that point. And then I know at -1 I have -2. And I know that's going to be a min, so I'm going to draw a little bump. Does that make sense? All right, so let's find the second derivative. We want to know where that point of inflection is. So I'm going to have y double prime is going to be 24x plus 36. So if I set equal to 0 and I solve, I get -36 over 24, which is -3/2. Okay, so the second derivative. And again, if you can kind of think through this problem, you don't have to plug things in. It's not hard to plug in like -2 into the second derivative. You can clearly see it's negative, and same over here, it's positive. But we also know that it's something like this, right? So it's clearly going to be concave down and then concave up. So it's not super important that we do that little graph there, that little number line, just as long as we know that there's a point of inflection happening at -3/2. Okay, so we need to find what f of -3/2 is. So if you go back to the original and you plug in -3/2, I already did this in the other classes, so I won't waste time doing it, you get -1. All right, so that point of inflection is directly in between those two values, which doesn't always happen. All right, and then the last thing we have are the intercepts. One of them is super simple, the y-intercept. You guys all know the y-intercept, right? So y-intercept, you plug in 0 for x. So when I do that, I have 0, 0, 0, 8, right? So my y-intercept is going to be 8. And then my x-intercept, that's where it gets hard. It's very difficult as a calc teacher or calc textbook writer to come up with functions where you can factor the first one, right, the original function, the derivative, f prime, and f double prime, right? It can be really, really hard to come up with functions like that. So in this case, it's kind of hard to factor the f of x. Do you guys see, like, you can't split the middle? You guys know what I mean with that? Like, I could try to split the middle, but I have 4 and 18, and the other one's 24 and 8. It's not going to work that way. So if we're trying to figure out where it's equal to 0 for the x-intercept, what we have to do is we set our y equal to 0. And we have to solve this equation. So do you guys remember how we did this, like in Algebra 2 and pre-calc? Dimitri, do you know? Not by factor, by grouping. We just tried that. It didn't work. It's my favorite theorem. If you really know me well, you know it's my favorite theorem. A rational roots theorem. Oh, Spencer knows me. All right. So yes, it's rational roots theorem. It's the P over Q. Don't worry though. You don't need to know this on the AP test. So this would be something where you'd have your calculator or whatever, so you wouldn't have to do it. But basically, you do a 2 here. Well, -2 actually, because we knew -2 gave us a 0, right? We already know that that's one of our x-intercepts because we already found it in a previous step. So we have 4, 18, 24, and 8. So when I do my synthetic division, I get that. I walked by Noah Williams the other day in the hallway, and he was telling his girlfriend, I love synthetic division. I was like, are you just saying that because I'm walking by you? And he was like, I didn't even know you were there. I love when I walk down the hallway and hear you guys say, I love synthetic division. So we get x plus 2, 4x squared plus 10x plus 4. And then that even factors, right? You can pull out a 2. And then you have 2x squared plus 5x plus 2, which factors into 2x plus 1 and x plus 2. So you have 3 x-intercepts. You have -2, you have -1/2, and then you also have -2 again. Does that make sense based on our graph so far? Do you guys remember multiplicity? Do you guys see how it bounces? Like it goes up, it hits it, and goes back down. It has multiplicity. Okay, so that is our graph. That is everything we'd ever want to know about our graph. Yeah. What is what? Yeah, so we have -2 from that one. Oh, why, how did I know to try -2 first? Because I'd already found this, f of -2 was 0. So I knew that it would factor evenly if I did -2. Yeah, kind of tricky. All right, so when you guys do these graphs, you only have 2 for your homework. I want you to label everything. So I would want you to go through here, and I would want you to label -2, 0, and put max, right? And then label the point of inflection, and label the min, so I can find everything very easily, okay? So PI, so it was what, -1, or -3/2, comma -1, and then min. And you can write them as points. You don't have to say a minimum of -2 at, you know, -1. All right, there we go. All right, so that's a polynomial one. Polynomial ones aren't that hard. They're pretty straightforward, right? So I didn't have any denominators or anything. All right, this next one's kind of weird. I like the weird ones. All right, here we go. So we have f of x equals x squared minus 3 all over x cubed. So when you guys first learned how to do product rule, quotient rule, power rule, all those things, I told you not to overcomplicate things. So you could make this one super complicated by doing quotient rule, but you don't have to, right? You could bring the x cubed into both pieces. So you get 1 over x, which is x to the -1, minus 3x to the -3. And now it's super easy to take the derivative. It's just a power rule problem. Okay, so let's do that. So looking at our original, our domain is x can't be 0 because the denominator. So that ends up being our vertical asymptote 0. So if I'm doing a little sketch, I have y equals 0, or x equals 0 as my vertical asymptote. All right, do you guys remember the trick for horizontal asymptotes? If it's powers, right? You look for your largest power, which is x cubed. And you look for any other x cubes on the top. We don't have any, so we put a 0. So we look at 0 over 1, which is 0. So y equals 0 is the horizontal. So vertical asymptotes you could never cross, right? Because it's not in the domain. You can't have a point there. But horizontal asymptotes are just talking about the end behavior. We talked about that yesterday. It's the limit as x goes to infinity and the limit as x goes to negative infinity. So you can cross horizontal asymptotes. Okay, so we go ahead and we find the first derivative. So the first derivative is going to be negative 1 x to the negative 2 plus 9 x to the negative 4. So I always have you guys like clean up the first derivative. So it's negative 1 over x squared plus 9 over x to the 4th. So we would multiply, we would get common denominators. We would multiply by x squared over x squared. So we got f prime of x equals x squared times negative 1 plus 9. So 9 minus x squared all over x to the 4th. Do you guys see what I did there? They're common denominators. And the reason we do that is because we get critical values not only from the numerator, but also the denominator. Like we could have something that's undefined, but we still have a max there, right? Think of like absolute value functions or corners or cusps or whatever. Okay, so our critical values are going to be plus or minus 3 from the numerator and also 0. So this is one that you probably don't know how to shortcut. You probably can't be like, oh, I know it's going to go plus, minus, plus, you know. Like we don't know. But we do know that 0 is a vertical asymptote, so I go ahead and I draw that in as a like dotted line. So I think, okay, I know I'm not going to have like a max or a min there because of that vertical asymptote. All right, and then we test. So when we test in the first derivative, let's say I plug in negative 4. Do you guys see that the denominator is always x to the 4th? It doesn't matter what you're plugging in for x to the 4th. It's always going to be positive, so we don't worry about that. We're just doing the numerator. So 9 minus 16 is going to be negative. But 9 minus 4 is positive, right? And then 9 minus, you know, if I have 2 squared again, 4 is positive, and then negative. So that means that we're increasing, or not increasing, we're decreasing, and then increasing. So there has to be a min at negative 3. And then we're increasing and we're decreasing. So there has to be a max at 3. All right, so we're going to find all those values. So I'm going to find f of negative 3, f of 3. I don't find f of 0 because that's an asymptote. So I go back into the original function and I find the y value that goes with it. So if I plug in negative 3, I get 9 minus 3 is 6 on top over negative 27, which reduces, if I divide by 3 on top and bottom, to negative 2 over 9. Then when I plug in 3, I get 6 over 27, which is 2 over 9. So this is going to be a really strange graph, and you'll see why when you draw these maxes and mins right now. Because I have 3, 2 ninths, and I said that that was a max. All right, so I'm going to have something right here, and it's going to be a maximum. And then I have negative 3, 2 ninths, and that's going to be a minimum. Negative 2 ninths. So it's like that. You guys see? It's kind of weird, isn't it? It's like, wait, is it going to cross that? And it can. It's allowed to cross the horizontal. All right, now, the second derivative I told you is not always super important. But in this case, it's a weird graph. It's like, wait, what is going on in this graph? So let's think about, you know, what we think is happening. Let's see if we can do without the second derivative. All right. With the vertical asymptote, we're always going to approach that vertical asymptote. So we think that it might be crossing the axis, right, and going along that. Does that make sense? Along the vertical? Okay. So you can actually determine if something crosses the axis without doing any calculus. And you guys might have done this in pre-calc. I don't know if you guys did or not. Did you guys ever talk about when it crosses the horizontal? Okay, let's think about that. What that means. If it's going to cross the horizontal asymptote, you're finding when you're function f of x is equal to the horizontal asymptote if it crosses, if it ever reaches that height, right? So let's write that. So let's see if it crosses the horizontal asymptote. So if I'm checking that, I'm setting my function equal to my horizontal asymptote. So I'm going to say that x squared minus 3 over x cubed equals the horizontal asymptote of 0. Does it ever equal 0? Sure. At x equals plus or minus root 3, right? And since the horizontal asymptote is 0, that's actually your x-intercepts. Negative 3 comma 0 and negative root 3 comma 0 and root 3 comma 0. So it definitely crosses. It's crossing at like negative 1.73 something and 1.73 something. So it's definitely crossing. And then it's going to go along that vertical. But we know that on the ends, the limit as x goes to infinity, it has to be 0, right? It has to go along that horizontal. So do you guys see how that's going to happen? It's going to do a little curve. It's going to curve back down and go along that. Does that make sense? Because it can't cross again, because we just showed that it only crosses in two spots. Is everybody with me? This is a really weird graph. Okay. So now I decide, do I really need to find that second derivative? Do you think you have any points of inflection? Yes, this is your question.
So is it just going to be a hole at the point of the rest?
It's not a hole. Yeah, you can cross horizontal asymptotes, yeah. So there's actually a point that does that. It's at root 3. Like if you plug in root 3, see how you get 0 and negative root 3. All right, so I want to figure out if there are any points of inflection. Where does it look like it's concave up, concave down, and so on? Can you guys see? I don't know how good you guys are at concavity. It's changing somewhere in here because this was concave down, but then it has to curve up to go along that horizontal. Do you guys see it? And this was concave up, and then it's concave down. So we should go ahead and find the second derivative because we need to know where the point of inflection is. All right, so if I'm finding the second derivative, again, just use the power form, right? Negative 1 x to the negative 2 plus 9 x to the negative 4. So when I take the derivative, I get f double prime of x equals 2 x to the negative 3 minus 36 x to the negative 5. So I need an x squared and an x squared on the top and bottom to get common denominators. So I have 2x squared minus 36 all over x to the 5th. So I end up getting 3 critical values. So from the denominator, I get x equals 0. No big deal. We already knew that one. Vertical asymptote. From the numerator, if I set it equal to 0, oops, minus 36. I get 36 divided by 2, so 18. I get x equals plus or minus the square root of 18. Which you can find as a decimal if you want, or you can write it as plus or minus 3 root 2. As a decimal, it might help to graph. So it's going to be like 4.243. Really running out of room. So 4.243. So that's actually going to be where your points of inflection are located. So if you plug that into the original, what do we get? I get 0.196. So my points of inflection, those occur at 4.243, comma 0.196. And then the other one occurs at negative 4.243. And if you plug that one in, you actually get negative 0.196 because it's an odd function, right? Does that make sense? So that's pretty hard. That's about as hard as I get. That's a pretty complicated one. Okay? All right, so let's try the next one. All right, so this one is a little tricky. So our domain is x can't be 2 and x can't be negative 2. That's starting out pretty easy. We'll do the easy steps first. So those are vertical asymptotes. Oops. What's the horizontal asymptote? y equals 1, right? Because you have x squared over x squared. Intercepts, if I find the x-intercept, I plug in 0 for y. So I end up getting 0 equals x squared. So x equals 0. And if I find the y-intercept, I also get 0, right? If I plug in 0 for x, I get 0 over -4, which is also 0. So 0, 0 is the only intercept. So if we go ahead and we find the first derivative, so take the derivative using the quotient rule. So we're going to have low d high minus high d low all over the square of what's below. So at the beginning of this lecture, I told you guys that the second derivative is hard to find sometimes. Okay, if you know a trick, it will save you a ton of time. Your goal in the end is to factor the numerator and the denominator, right? You want to find the critical values for both the first derivative and second derivative. Okay, so instead of multiplying this out, as some of you are, because I can already tell Audrey is already multiplying it out. Are you doing that? 2x cubed minus 8x. You can do that, that's fine. But the quickest way, all the time, will be to look for a common factor. Okay, so see how you have a 2x in common? So we can pull that out. Okay, and it's not really a big deal on this one. It's pretty quick anyway if you don't. So I have x squared minus 4 minus x squared. So that becomes a -4 times 2x. So I'm going to get -8x over x squared minus 4 squared. All right, but the time when it will save you a ton of time is when you have something like that on the bottom. If you had a cubed, then you're doing a lot of chain rule. You're going to have things that you would have to FOIL out. It would get crazy. So know that shortcut. So write yourself a little note. Always look for a GCF on these derivatives. All right, so if I'm finding critical values, I'm finding it from the numerator and the denominator. So I'm going to have x equals 0, and I'm going to have 2 and -2. And the 2 and the -2 are no big surprise because those are the vertical asymptotes, right? So we'll do little dotted lines for those. And then 0, we don't know. So I'm going to test in each location. So if I try like -3, when I'm testing, it's really not that bad because the bottom is something squared. So it's always positive. Okay. So if I try -3, I get -8 times -3 is positive. If I try -1, -8 times -1 is positive. The bottom is positive regardless, so I don't have to worry about it. All right, if I plug in 1, I get negative and negative. So that means I'm increasing until I get to the vertical asymptote. Then I'm increasing again and decreasing. So what happens at 0? It's a max, right? And it's at 0, 0. If you plug in 0, you get 0. And then it's decreasing again. So if I'm graphing what's happening here, at 0, 0, we have a max. So we can draw like a little bump there. But we also know that it's going to go along the vertical asymptotes. So it's going to look like that. Okay. Second derivative. Okay, here we go. Are we ready? Write tiny. F double prime, don't you love when your calc teacher tells you that? That's when it like takes up a whole board. So we have low, d high is just -8, minus high, d low. So d low is going to involve the chain rule. So we're going to have 2 times x squared minus 4, all raised to the first, and then times the chain is 2x. All over the square of what's below. So I'm going to have x squared minus 4 to the 4th. So this is what I was telling you can be terrible if people don't know the trick. Because they're FOILing out the x squared minus 4 times itself. They're multiplying by -8. They're multiplying all that crap on the right side together, right? It takes forever. It's awful. Don't do it. So what we do instead is we look for a GCF. So what do we have in common on the top? We have a -8. Do we have anything else? Yeah, one of those x squared minus 4s. That's what's going to save you. Okay, so when we pull it to the front, we have a -8, and we have that x squared minus 4. And then in brackets, we have another x squared minus 4 which I don't need in parentheses anymore, I guess, because it was times that -8, which we already pulled out. And then I have a minus, and I have 2 times 2x. So I have minus 4, or well, I have x. Negative x times 2 times 2x, negative 4x squared, right? And then I have x squared minus 4 to the 4th. So what really happens is one of those x squared minus 4s ends up canceling with one of them on the bottom, and we end up with x squared minus 4 cubed. So we have -8, and then we have negative 3x squared minus 4. So that's a lot of negatives. Do you guys see what I'm saying? So I have -8, and then I have negative 3x squared minus 4. So let's just make them positives. Right, pull out a negative, and then it's all positive. So our final answer is going to be 8 times 3x squared plus 4 all over x squared minus 4 cubed. Okay, that was a lot of work. Do you guys agree? It was terrible. And you could have things that have, like I said, like raise to the 3 on the bottom. It will be terrible. Like finding the second derivative is a hot mess sometimes. We do not want to do it. So if we can avoid it, that's the best way. So maybe I didn't need to do that. So you hate that one. I'm like, okay, let's spend a lot of time doing this, and maybe we didn't need to do it. Think about how we did this in Algebra 2. Okay, what we did is we needed to know, like we knew the vertical or the horizontal asymptote was here. We needed to know what happened on the right and the left side of the graph. So what we did is we did a little t-table, and we plugged in something on the right of the horizontal or of the vertical asymptote, so 3, and plugged in something on the left, -3. Well, that's really easy. Go back to your original. Plug in 3. We get 9 over 9 minus 4 is 5. And then this one is 9 over 9 minus 4 is 5, right? So we get 9/5, 9/5. So we have almost at 2 for both of them. But we did have something weird on that last one. Do you guys remember number 2, how it crossed the horizontal? That could still happen, right? My guess is that it goes like this. But we really should verify that it doesn't cross the horizontal. So that's what I was showing you guys before. If you're trying to decide if it crosses the horizontal, set your function equal to the horizontal asymptote. This is super fast. You'd have x squared over x squared minus 4 equals 1. When you multiply that x squared minus 4 over, you get x squared equals x squared minus 4. What happens when you subtract the x squareds? What do we get? 0 equals -4. What do you think that means? It doesn't cross, right? It does not cross. So we're good. That is your graph then, for sure. So see how that, I mean, it's still annoying. You still have to check to see if it crosses. You still have to do a little tiny t-table, but it's much faster than finding the second derivative. Okay? So if you need to do that on your homework instead, I would do that. All right, and the last thing we're going to talk about is using your calculator to help you. So 2/3 of the test is non-calculator, right? So you have to know how to do it without a calculator. All right, but some of the questions do allow you to have a calculator, so we should talk about it. Okay, so it says on the AP Calc test, many questions can be solved using graphing calculators if allowed. So you guys just had a homework assignment where I let you use your calculator. Did you guys find maxes and mins using your calculator? Yeah, did you find the x-intercepts using your calculator? That is exactly what you should do. Don't try to power through it like Jack Paganelli tried to do everything by hand. I appreciate his excitement and spirit for calculus, but don't do it all by hand. You need to know how to use the calculator too, okay? So make sure that you use correct windows. You're finding the maximums, minimums, and zeros, and so on. So it says estimate intervals of increase and decrease, intervals of concavity, find the extreme values, and find the inflection points. So we're just going to use this, and we're just going to graph everything, okay? So as I'm taking, well, let's go ahead and try to graph this original one. So go ahead and enter your calculator. Everybody get your calculator out and do it along with me. Oops. I really want to move that, but it's not letting me. Here we go. All right, so we're going to put in, you guys will be faster than me, it takes me a bit, so x raised to the 6th minus 15x cubed. No, 15x to the fifth, right? Plus 75 x to the fourth minus 125 x cubed minus x. Okay? If you need a calculator, I have one on the front desk too. If you need one. All right, and we hit graph. And let's say you're on your normal Zoom 6. Oops, Zoom 6. Okay, you're on your standard window, so most of you guys are on that. I don't know what he just said. Okay. I thought he said I just left. I'm like, you still in the room, I know. All right, so this is not the best window. Do you guys see? So a lot of people that have taken stats before always scream at me, do Zoom Fit, do Zoom Fit. And Zoom Fit works sometimes, but rarely. So you can try it. Do you guys know what Zoom Fit is? So Zoom Fit is down here. So Zoom 0. But it still doesn't give you a good window. So it's not helping. So you really have to know how to find a good window when you're using your calculator. Okay, so right now I can kind of tell that you can see where it's going back up, right? And that's an x to the, we have an x to the 6th graph, so the ends are definitely going to go up. I know that I'm seeing most of it for the x values. But for the y values, I have no idea what's happening down there. It looks like it's totally flat to me, and I know it's not. Well, that's because when you look at your window, look at what the window is. It's crazy. So we don't want it to be that. So let's say we make the y min negative 200 and the y max 200. And then we try it from there. So when we hit graph, it's still going to be pretty close, but we're going to cut off part of the graph. Okay, see how it doesn't quite see that minimum? We want to know what that minimum is. Okay, so what we're going to do is we're going to do a second, or we're going to do a window again and go down to negative 300. Okay, and that's good. Let me turn off the light so you can see this better. So you can go ahead and you can find that minimum. We're going to have to find it anyway, might as well, right? So go ahead and find the minimum using your calculator. So do second trace minimum. Okay, and you're going to go down there, and you're going to do left bound, so get on the left side, right bound, get on the right side, enter, go to where you think it is, hit enter. So we get 2.504, negative 246.643. So if I'm drawing a little rough sketch, I don't know what's happening there. I don't know what's happening here, but I know that this is 2.504, comma, negative 246.643. Okay, but the question is, what's happening here? Because we are super zoomed out, okay? We are between negative 300 and 200 for our y values. Okay, so right here, we don't know what's happening. It could be coming down, and then it could be going slightly up and then back down, and you could have a minimum and a maximum there. Okay, we don't know what's happening. Okay, so you could try to zoom in. And I always use my favorite zoom method, Zoombox. Have you guys ever used Zoombox? Oh, it's great. Okay, so everybody try this with me. So you're going to hit zoom. It's the first option, Z-box. So this is when you want to zoom in on a particular area. So what I'm going to do is I'm going to move my cursor. It was over by the minimum. So I want to zoom in on just this, like, really close to the origin. Okay, do you guys see where my little cursor is? Can you see it? All right. And when I get to what, I'm trying to make, like, zoom in right here, this little box right here. So I'm going to hit enter one time. And then I'm going to arrow over, still not hitting enter, until I arrow down and get a nice little box shape. Do you guys see? And even when you go over and down, you can still adjust it. You can, you know, make it smaller if you want to. Right? And then once you get that second corner, then you hit enter again. And it takes whatever you had and it zooms in on that perfect rectangle. Isn't that cool? So if you're ever like, I don't know what's happening there. But even when I do that, I still can't tell. Can you guys tell what's happening? I can't tell if there's a minimum or a maximum. And you could try to like trace and you could try to find the minimum and maximum, but we still can't tell. So that's when we graph the first derivative. Okay, so go ahead and graph the first derivative. Let me go ahead and write what the first derivative is so I count myself. Can't you tell? Is that what you said? I don't think that, yeah, I don't think there is a maximum in there. It didn't look like there was to me, but you never know when you're like way zoomed out. Because if you check your window there, it's still really zoomed out. All right, so we're going to have 6x to the 5th minus 75x to the 4th plus 300x cubed minus 375x squared minus 1. So that's our first derivative. So we're going to put that in. All right, and I don't want to graph the first one anymore. I just want to look at the second derivative. So I'm gonna go up to y1. Do you guys see how I'm on top of the cursor, like on top of the equal sign? I mean, and I hit enter, and it deselects that equal sign. That means it's only going to graph y2. Okay, and I'm just going to go for my window. I'm just going to do zoom 6 again, back to my standard window, because I'm trying to figure out where my y prime is equal to 0, if there's any maximums or minimums in this curve. Okay. So if I graphed f prime, what it looks like, can you guys tell? It kind of goes up really close along the axis, and then it goes up, it crosses, and it comes back down. It's kind of hard to see. But don't think of it that way. Think of it the way that we are familiar with it on a number line. Where is f prime equal to 0? It's equal to 0 at this place where it's crossing the x-axis. So let's find that value. Okay, and what do you guys think that it's going to be? Like if we do second trace 0. I'm going along here. Any guesses? Always look at your y values too. See how it's negative, and then I want it to be positive, and then guess. So I go to the closer one. Look what it is, 2.504. Does that make sense that it's 2.504? Yeah, the slope is equal to 0 there. So we're good. That's the only place where it is. So what that means about the rest of our graph, right? So at 2.504, we had a slope of 0. And we were below the axis for f prime, and then we were above the axis. So it means we were always decreasing and we were always increasing, except to that one point. So when you look at this curve, right, so look where I'm going to trace in blue. We're always decreasing. We don't taper off to a slope of 0, right, and then go back down. It's not like an x cubed graph. And we don't like make a max or a min, right? Does that make sense? It's always decreasing. All right, and then the same thing on the right side, it's always increasing. Okay? So the last thing we need to find are points of inflection. So we would do that same method. We would find f double prime. So we get 30x to the 4th minus 150x cubed plus 900x squared minus 750x. And we would find what's happening there. We would find when it's positive and negative and so on. Okay, does that make sense? I'm guessing it's up, down, up, down, up. Can you guys kind of tell with the concavity? What did I do? 75 times 4? Oh, yeah, I did times 2, didn't I? So, yeah, minus 300, thank you. I was too speedy. So there's basically going to be 4 places on your second derivative. When you find your second derivative, you're going to have 1, 2, 3, 4 places where you're going to have values where the second derivative equals 0. So you're going to find you're going to graph that for y1, and then you find where it crosses the x-axis. And you'll see that it will be concave up, down, and up. Okay, so you can do that part, but we'll kind of skip it. It takes a while to graph. All right, and the very last problem talks about, well, is there a way to kind of shortcut it? What if you don't know how to find the derivative? Can you graph the derivative on your calculator? And you actually can. Okay, so it says sometimes it's really hard to find the derivative. Like x raised to the sine of x, you would actually need to do logarithmic differentiation. But then it's like, wait, now how do I solve for y though? So you can do it, but it's a little bit difficult. Okay, so what we would do then is we put in y1 as x raised to the sine of x. And then y2, we would use n deriv. Okay, so n deriv is going to put it one of two ways. So the old calculators will say this. So we would want it to say y1 and then x and x. But the new calculators are going to say dd, and you put in an x. And then you do y1, x equals, and you put x. Okay, so let me show you that. So I'm going to clear out of these graphs here. Okay, so we're going to do x raised to the sine of x. So that's our y1. And then for y2, you can graph the derivative by doing math 8. That's our n deriv. And then this is a newer calculator, so it says like that. And you could go ahead and you could type in y1 all over again. But if you already have it in the y1 spot, you hit vars, y bars, function, y1. And then we want evaluated at every single x value. So when you hit graph, it will graph, like if I wanted to only graph the derivative, it will graph it for you. So you can deselect that and hit graph. It just sometimes takes a really long time for it to graph. So then you could find the zeros, you can find maximums of the derivative, and so on. Like you could do all of that work. Yeah, mine's still thinking. All right.
So for the older calculators, you do y1.
Yeah, you would do y1 comma x comma x. The derivative's not showing up because it's probably outside that window, but there's the first one. All right. Actually, I might have it in degree mode. Is it in? Does yours show up? Did you guys try it? Sorry, this calculator I always go from pre-calc to calc. Oh, it's still thinking. Yeah, I'm in degree mode. That's what the problem is. Radians. All right, so hit graph, and then it works. All right, so on your homework. I only have 2 things for you guys to do. Okay, so I have 2 problems for you to do, but I want you to label everything nicely. Okay, see how it did the first one, y1, and now it's doing its derivative. Okay, so you can find all that information.